Topping the news today for the International Space Station, a set of small amateur radio satellites that hitched a ride to the orbiting complex aboard the Japanese H-2 transfer vehicle back in late July are being released into space. That demonstrates another capability of the space station, as well as the science each satellite is dedicated to research.
CubeSats, small satellites designed to perform short-term but critical functions while orbiting the Earth. The number of CubeSats and small satellites placed in orbit has been growing exponentially since 1999. Hundreds of CubeSats were launched this year from the United States alone.
3, 2, 1, ignition. We have orbital sciences operating.
Many more are expected in the near future from the now expanding number of spacebound nations.
Originally, they were looked at as educational toys. A metric satellite, in order to focus our students' attention on metric system, that's university-wide in America. However, Earth observation, environmental monitoring, the CubeSat is proving itself in ways that were heretofore unexpected. So what we're looking at now are increased opportunities to fly these CubeSats.
And NASA put out an open call for CubeSats that can operate for weeks, maybe months, for deep space communications in the extreme environment near the moon and beyond.
Moore's law, which diminishes the size of electrical components, has really come in handy. Miniaturization of electronics has really been the lynch mark for the success of the CubeSat. And as that has taken hold, we're able to put more and more interesting payloads into these very small satellites. This is the basic CubeSat form factor. The CubeSat standard is a 10 centimeter on a side, which is 1 liter, of course. And the mass is 1 kilogram, which is the mass of 1 liter of water. And the availability of commercial kits, I think, is going to revolutionize the accessibility of this form factor for students who are interested in building their own satellite to go into space. Once you have a form factor like this, here's a single U, as we talked about earlier, then it's possible to look at other experiments in different sizes. So that's a 1U. This would be a 2U, obviously 2 cubes together. And then there's also the possibility for a 3U as well. And that does allow for the possibility of larger payloads, of more sophisticated payloads. What we've done here is taken a commercial off-the-shelf CubeSat kit. You still need to build some things yourself, in particular your payload. So what we've done here is to buy off-the-shelf computer, an off-the-shelf comm system, and an off-the-shelf electrical power system. And then we've built our own solar cells, panels here, and our own payload. And you can see on the top there's a sun sensor, 4 solar cells, and temperature sensors. As you can see on a CubeSat, we don't have all that many power solar cells, so we have to manage the power very carefully. In order to packetize the CubeSat and to make it easy to launch, they've come up with a container for it, what are called P-pods, the Poly Picosat on-orbit dispenser. The standard container will fit 3 CubeSats or 1 3U CubeSat. And then it has a door on it like a jack-in-the-box, and when it opens, there's a spring which pushes the CubeSats out upon command.
NPS has since developed its own CubeSat launcher dubbed NPS Cool. It has served as an auxiliary payload on a number of missions, launching dozens of CubeSats into orbit.
The signal gets sent to each of the P-pods through each of these 8 cables, which are connected to each one of the P-pods. Each cable has a power and a redundant power signal and a deployment signal as well to make sure that the door is closed throughout launch. The switches on the P-pod are right here. They're really small. There's 2 on each for redundancy. These are the door stoppers on the P-pod, and they prevent the door from swinging all the way out. Each of the P-pods has an NEA on it, and that's the actuation device, and it's a non-pyro signal. And it's just an electrical signal that opens the door.
The vastly different systems in CubeSat development has hindered the speed in which these small satellites can be utilized. If CubeSats are to prove useful beyond a case-by-case basis for government application, there must be some standardization.
By agreeing upon a standard size, they're able to make a standard container to deploy the CubeSats.
In response, Jim Newman and others from NPS's Space Systems Academic Group, Lawrence Livermore National Laboratory, and National Reconnaissance Office have proposed a basic CubeSat structure. According to the researchers, the CubeSat bus reference architecture has application to software, electrical, and mechanical interfaces. Its aim is to provide a flexible platform, allowing for interchangeable components and faster construction, a design that can also be endorsed by industry. In 2015, NPS will take the next step in CubeSat development and will serve as ground control for a number of missions, including Falcon Sat 7.
CubeSats are finding greater acceptance among national organizations in our country. They'll never replace national systems. It's very important to remember that for certain Earth observation activities and other things, you need large satellites. However, this idea was to also make space more accessible by making a very small form factor, which should reduce the cost and perhaps increase the availability of opportunities to get satellites into space.